Okay, great. So the recording has started. So I was saying, before we start, I think it's important for you to be aware of the fact that you need to put in a lot of work this year. So I'm not sure if last year you were, and if you were, then thumbs up. This year you might need to put in a bit more work, you know. Specifically for maths, my advice is it's not the hardest course. And at the same time, it's not the easiest, you know. Hard is relative. It depends on your strengths and also on your weaknesses. So my advice is after the session, you can always rewatch what we were doing. But just in general, start working because you do not have a lot of time, you know. When week one starts, you'll be trying to find where you stand, and you might find yourself still trying to find out where you stand even after 3 weeks. So please try your best to start working early. And the benefit of starting to work early is it buys you enough time. Just give it some thought. So one thing you should realize is that when we are looking at vets, the reason why you will fail a course, let's say for example, like math, is not necessarily because of complexity. You know, it's not because the work is hard to understand, but it's a number of factors which are involved. So we are looking at a multivariable equation when we are looking at passing in general. So for you to pass, we are looking at 3 variables, which I can think of. So you need to understand the complexity. And you understanding complexity has never been the problem. But now, when we are looking at second year, there's complexity. There is the work overload. So meaning there's a lot of work which you need to do. Because at minimum, I think the people who are doing the smallest number of modules, they are doing 9 modules. So you're looking at complexity of the work. You are looking at the work overload, and you are looking at time. You don't have a lot of time. So trying to balance these 3 things at the same time in real time is not easy. So that's why I'm saying my advice is you can buy yourself time by starting to work already, because there's this week and there's also next week and one day on the other week before you open. So if you can at least take 2 modules and say, let me do week 1 work, you know, you can use your drives, which are there in groups. At least when you get into week 1, while others are still trying to find their feet, you will be understanding their work more because they are trying to find their feet and they are also trying to juggle the complexity of the work and the work overload. So you'll be having a week's advantage then, of which you should try and keep that week's advantage up. And if you can, just increase it. So you should start working as soon as you can. Because the reason why you'll fail is not because the work is complex. We are looking at a multivariable equation. So there's complexity, there is the overload, and then there is time. You don't have a lot of time. So balancing these 3 things is what actually makes people pass, you know, because complexity alone is not enough to defeat you. But now when these 3 variables combine, it's really hard to work with. So my advice is before we start working as soon as you can. You don't have as much time as you think you do. And it would be sad for you to realize 3 weeks into March or 4 weeks into March or 1 week into April, test week kicks in. That's when you realize that actually I don't have a lot of time. So the earlier you start working, the better. Any general questions before we start?
Sir,
Yes.
I heard you like mentioning drives. Like, what are those?
Mentioning what?
Drives, something like drives.
Oh, yeah. So I mean Google Drive. So you see, let's say, for example, you start in CAM, there's many of them which are floating around. So essentially, your Google Drive, it's where one of the students, a previous one, decided to upload material which is related to the course which you'll be doing. So if you can get access to those links, then you can use your PC, go there and then see, okay, there's maths. So for maths, this is what is going on. There is, say, process if you're doing CAM. For process, this is what is going on. And then you start giving yourself an overview because you really don't have time, you know. It sounds scary, but the sooner you realize that you need to start working, the better. You'll thank yourself later. So you'd rather not enjoy this week and the coming week and try to find your feet and not be stressed when week 1 and week 2 comes than for you to enjoy now and be stressed when week 1 and week 2 comes. And then you'll find yourself 2 weeks behind. So please check with your seniors, and you can also just drop a message in the group, the WhatsApp group, pertaining whatever course you are doing. You know, let's say you are doing chem and you are like, anyone who has a chem drive, I can drop some. And from the other school, I can even ask some people to share. So you should start working. Okay. Any other question? Great. If we all okay, then let's go to the business of the day, which is complex numbers. And complex numbers are not complex. So let's see. So this is what I shared yesterday. And I hope all of you had a chance to have a read and see what the case is, which I was trying to make here. So as easy as it might look like, actually you are also going to use complex numbers to do exactly this. So here I was trying to factorize. So let's zoom in. Okay, so let's zoom in here. So why complex numbers? And then I said, let's make a case, you know, from fundamental mathematics high school. So the base case is, we know that y is ax squared plus bx plus c. So if ax squared plus bx plus c is equal to 0, then we know what x is. That's your quadratic formula. Then building case, we said, look, so now let's say they give us x squared minus 1 is equal to 0. That's what we are trying to figure out. So how can we solve for x if x squared minus 1 is 0? So clearly here we could have just said x plus 1, x minus 1. That's factorizing. Then we equate to 0 and solve. But I was like, okay, let's use the quadratic equation. So we know that x squared minus 1 is the same as 1x squared plus 0x minus 1. We can see the a, b, and the c. We just plug them in, and we get our answers. Our x is either 1 or our x can either be positive 1. So we can plug positive 1 there. When we square it, and minus 1, we'll get 0. If we plug negative 1, square it, minus 1, we get 0. Great. So it's nothing but groundbreaking. We know this from high school. Now the last case, we are now saying, look, so we now have x squared plus 1 is equal to 0. And essentially how you think of this is, which number can we square, and after squaring it, add it to 1 and get a 0? So if you phrase that question that way, it really becomes interesting, because you are like, there's a number I need, which I will square, and after squaring that number, I will add a 1 and I should get a 0. Which number is it? And we use the same argument, you know, x squared plus 1 is the same as 1x squared plus 0x plus 1. And we can find our a, our b, and our c. And we use our quadratic equation. and we get here. So when we get here, the problem is we are now facing the square root of a negative number. Well, we know we can break that square root of -4 to this exponential laws. And we end up having 2 times the square root of -1. So this is the problem. For many years, we have been saying, look, the square root of a negative number is undefined, and we have been doing just okay, and we've been getting distinctions when we're still thinking the square root of -1 is just undefined. It is wrong maths. So fast forward, the square root of -1 is just it's imaginary, because we are engineers, so we cannot be always saying, the square root of a negative number is undefined. At the end of the day, we need to do these calculations and get these things working. So we cannot say when we see the square root of a negative number and say, look, so we stop. Everything is wrong and it's undefined. No. When we see the square root of -1, we'll just put I, or we'll put J. So those who are doing EIE will mostly use J, because I is for current for them. Now, with this in mind, we clearly see that we need to introduce, complex numbers, because we can't run away from negative square roots. So that's where the idea of I comes from. And when we see I, we think of complex numbers. Okay, so this was yesterday. Let's look at what we have today. So let's zoom in. So where we start is, this is where we start. So I is the square root of -1. This is the big deal. It's the first. And from here, all what we need to know is wherever we see I, essentially that's just the square root of -1. Can you guys see my screen?
Yes, we can see it.
Okay, great. So enough about the I. So when we are looking at complex numbers, we have not different types, but we can classify them. So we have what we call the real imaginary form. So when we're looking at the real imaginary form, all what we are looking at is we are looking at a complex number, Z. It is X plus I, Y. Easy. And what we are looking at here is what we call the real part. And what multiplies the I is what we call the imaginary part. Okay, someone is not muted. Please check your mic. You might be the person. Thanks. So when we're looking at a complex number, we have the real imaginary form, and it looks this way. So we have the real part, which is X, and the imaginary part is whatever which is being multiplied by the I. So let's just take an example. So if we are looking at Z is 3 plus 4I, the real part of Z is 3. And the imaginary part of Z, the imaginary part is whatever is being multiplied by the I, and that is a 4. Easy, isn't it? And when we look at the real imaginary form, there's an operation which we need to look at, which we call it conjugation, or they usually call it just conjugate. So let's look at what this means as an operation, because you need to know it. And how this is eventually going to tie up at the end of the day is that you will need to factorize complex numbers or factors which you cannot factorize using your quadratic equation. That's where your complex numbers knowledge will come in. So this is just an operation. So when we conjugate, e.g., so let's say we have a complex number, we are still looking at the real imaginary form. It is x plus iy. When we conjugate, which we indicate by the dash on top, is all what we do, we change the sign of the imaginary part of the complex number. So x is the real, I, the imaginary part, we change the sign, it becomes negative y. So which means we have x minus iy now. That's what we mean when we say conjugate. So let's do just a short, quick example. So let's call it this one, let's call it example 1. Let's call this one example 2. So if I'm given z is 2 minus 2i, and they say to me, find the conjugate. So the conjugate of z, we said we indicate by the dash on top, is going to be 2. Is that we change the sign of the imaginary part. So the imaginary part, we can clearly see it is negative 2. So if we change the sign, we should get a positive 2. And this is the conjugate. Easy. Now, let's take this knowledge of what a conjugate is, which is just changing the imaginary part of a complex number. Let's take it to the next page and see if we can deduce a property which will later be useful. And we are still looking at the real imaginary form. So let's look at your conjugate and see if it's going to give us a property. So some of these you should try and know them by head. So your z is x plus iy. Clearly, this is still the real imaginary form. And your conjugate is x. We change the sign of the imaginary part. So it is plus y. Now it's going to be minus y. So when we multiply complex numbers, let's multiply z and z dash. So we're multiplying z by its conjugate, which means we have x plus iy times x minus iy. So here we can do our good high school FOIL. So let's quickly work that out and see what we get. And this is what you need to take and know it for the entire year. You can. In fact, you all can, or you should. So x times x is x squared. And then we have x times negative iy, so it becomes negative I xy. Then now we come here. We have iy times x, so it becomes positive I xy. And then we have iy times negative iy. So let's see what that means. Let's push this down. So one thing you should note is that your I times I is negative 1, and this should make intuitive sense. I times I is negative 1, because remember that I is simply square root of negative 1 times square root of negative 1. So the square roots, this is more like the square root of negative 1 squared. So the answer should be minus 1. So when we see I times I, what we get is negative 1. So now we have iy times negative iy. So the I and the negative I, when we multiply them, we are going to get a positive 1. So we have positive 1 times y, which is y squared. And these we can clearly see they do cancel. And what we obtain is now x squared plus y squared. And what you need to remember is the modulus of z. So the modulus of z, which is more like the magnitude, let's say, it is equal to the square root of the real part, which is x, plus the imaginary part, which is y. This is the modulus of a complex number. So if you look at our z times z bar, its conjugate, it's more like you got the modulus squared if you look carefully. So when you multiply z and z bar, what you actually get is the modulus of z squared. Because if you square this, you now get this. So that means z times by multiplied by its conjugate is simply the modulus of the complex number squared. That's what it is. So this you need to note down. Let me highlight it in red. So when you're working problems out in the future, or in a few weeks' time, or a month's time, this should come as second nature. When you multiply a complex number by its conjugate, you simply take the magnitude of the complex number and you square it. Or you simply square the real part and sum it with the imaginary part squared, which is what is going on here. Okay, for example, this should be 3. Okay. So if you have z is equal to 2 plus 3i, and we are looking for the magnitude of z, we can all agree that the magnitude of z is simply the square root of the real part squared plus the imaginary part squared. That's what the magnitude is. And this, if you do the summation, that's going to be 9 plus 4, which is 13. That's the modulus of this complex number. And what is also important to touch on is that you can actually add complex numbers, multiply them to FOIL, and subtract them and do whatnot. So let's take one example each. So let's say adding complex numbers. So if you're looking at z is, let's say z1, it is x1 plus I y1. And let's say we have z2, and it is x2 plus I y2. Then z1 plus z2, all what we do is we group the real part. The real part is simply x1 plus x2. And we group the imaginary part, which for z1, it is y1, for z2, it is y2. It is this easy. So a quick example would be, so let's say we have z is negative 4 plus 5i. And then we have, this is z1. We have z2 is 3 minus 7i. So if we are required to find z1 plus z2, all what we do is we have negative 4 plus 5i plus 3 minus 7i. We group the real parts. We can see these, they can be easily grouped and they give us negative 1. And we group the imaginary parts. So 5i minus 7i, we get negative 2i. And that's how you add these complex numbers. Easy. So let's look at subtracting them. So let's consider having exactly the same complex numbers. Let's copy them. So now let's say they are saying we should find Z1 minus Z2. So this means we have -4 plus 5i minus 3 minus 7i. And this, we can clearly see it will be -3, -3, and -4 will be -7. Then the negative will make a positive with the 7i. So we're looking at 5i plus 7i. 5 plus 7 is 12. So we're looking at 12i. And that's how you would subtract these complex numbers. Let's look at multiplication and then look at division. So multiplication, or let's say let's take exactly those and do Z1 multiplied by Z2. So let's quickly do our FOIL here. Let's see. So what we get is -4 times 3, that's -12. -4 times 7i, 2 times 4 is 14. By 2, 28. So we're looking at 28i. And then 5 times 3, that's 15. We have 5i times 3, that's 15i. And then now we have 5 times 7. 5 times 7 is 45, if I remember well. And I times I, we know it is -I, but there's a negative there, so it's positive. So we're getting positive 45. Now we can group the real and the imaginary. So here's our real, and the imaginary parts are the ones which are being multiplied by 8. So 45 minus 12, that's 33, plus 28 plus 15, it is what?
That 43.
Yep, 43i. And this is how you do your multiplication. So let me just underline these. And the interesting part is the division part. And that's what you are going to use this year. Well, it will come up now and then.
I have a question. Is it
It's
not, is a 5 times 7 not 35?
5 times 7, 5 times 6 is 40. 5 times 6 is 30. Yes, you are right. So it is 35 instead of 45. Thanks. 3, 5. So if that's the case, then I need to put a 2 here. Did I get it right? Yep. Okay, thanks. So let's look at division and see what we need to do when we divide complex numbers. So let's go. Any questions so far? So let's look at division. So let's consider a case where Z1 is X1 plus I, Y1, and Z2 is X2 plus I, Y2. And we are now faced with a case where you need to do Z1 divided by Z2. So this how it looks is X1 plus I, Y1 divided by X2 plus I, Y2. So one thing you should register in your head is we dislike division. Or let's say we dislike division of complex numbers. So when you see complex numbers dividing one another, your brain should ring, we need to do something here because we dislike division of complex numbers or dividing by a complex number. We dislike it. Your brain should fire, we need to make sure this never happens. And there's one way we can make sure we remove division by a complex number. And how we can do so is by multiplying by the complex conjugate of the complex number, which is on the denominator. Let me write that down and it will be apparent when I do it. So let me say multiply the numerator and denominator by the conjugate of the denominator. Okay, short. So this is all what we need to do. So we said, look, we dislike division of complex numbers and you need to come up with a solution. You can't dislike things and not do anything. And what we are proposing is what you should do then is multiply the numerator and the denominator by the conjugate of the denominator. And how that looks is, let's copy this. All what we do is an easy step and we are done. There's no need for us to deal with the division of complex numbers. So what we need to do is multiply by the conjugate of the denominator on the numerator and on the denominator. Let me see, multiply the numerator and denominator by the conjugate of the denominator on point. So that means the conjugate of the denominator, we can see it should be this. Because conjugate, remember we said we change the sign of the imaginary part. Okay, so this is going to give me a problem. My x appears like that. So my multiply is going to be a dot, rather. And we also divide and we also multiply by it also on the denominator. Okay, cool. So what we now have is, look, we now have Z1 over Z2 equaling X1 plus I, Y1, X2 minus I, Y2 divided by X2 plus I, Y2 times X2 minus IY2. So on the denominator, you just need to zoom in. So we can see we are multiplying conjugates here. And what we said before was that when you multiply a complex number, what we observed previous pages, by itself, the answer becomes the real part of that complex number squared plus the imaginary part of that complex number squared. So which means we can actually simplify the denominator and it no longer becomes complex, there's no longer any I, because our Z1 over Z2 will be the numerator. Let's multiply. Well, the numerator, you know how to multiply complex numbers, so let me leave it as it is. So the point is to get across the concept x1 plus iy1, x2 minus iy2. So now here, this is what we noted when we were multiplying a complex number by its conjugate. What we saw is that actually the answer is simply the real part squared plus the imaginary part squared. And now when we look here, the denominator, okay, here's our complex number. What is the real part squared? Well, what is the real part? The real part is x2, so we square it. What is the imaginary part? It is y2, and we square it. And that's how this fits. Okay. And now your division is simply by a real number, and we no longer have any division by a complex number. So this now looks friendly. And you can now multiply the numerator, separate it to its real and imaginary form. So let's take the Z1 and the Z2, which we had, and see how we can work around this. So let's take them. Okay, so let's do Z1 divided by Z2. So how that looks like is -4 plus 5i, which looks like S, divided by 3 minus 7i. So we now look at our statement. We said, look, we said we dislike division by complex numbers or of complex numbers. Now what we need to do is multiply the numerator and the denominator by the conjugate of the denominator. So that means we need to come here and say multiplied by 3. The conjugate of the denominator, we change the sign of the imaginary part. And remember, imaginary part is whatever which is being multiplied by the I. So it was -7, now we need to get a good +7. And we multiply the numerator and the denominator. So we need 3 plus 7i here. So when we go down, our Z1 over Z2 becomes -4 plus 5i, 3 plus 7i, divided by 3 minus 7i, and 3 plus 7i. So what? The denominator, we see we're multiplying complex conjugates. So instead of doing the FOIL process, we know we have done it before. When you multiply a complex number by its conjugate, the answer is simply the real part squared plus the imaginary part squared. So let's deal with the numerator first. So Z1 over Z2, this is equal to. So let's do our FOIL, which the more you do it, you should be able to do this thing off your head. Just look at this complex number and write it down. So let's see. we are sitting at negative 12, that's negative 4 by 3, and negative 4 by 7, that should be negative 28. But there's the I. And then now we are looking at 5I plus multiplied by 3, that's 15I. Then now we are looking at 5 times 7, which is 35, and we have I times I, and I times I, remember we noted down, it becomes negative 1. So this becomes negative 35. And then we divide by. So remember, the numerator, you're multiplying two complex numbers. One is a conjugate, and the other one is the original one. And the answer, we said, it's the real part squared plus the imaginary part squared. That's what you get when you multiply complex conjugates. So finally, our answer, Z1 over Z2, is 35 and 12, 7, so that's negative 47. And then that will become minus, let's see, it's going to be 13I, divided by, we have a 9 plus 49. And when they say separate this into its real and imaginary form, let's see, because that's what they usually would want to see, 13I. So this is 58. So when we write this, we would write it as negative 48, not 48, sorry, 47 over 58 minus 13I over 58. And now we can clearly see what is real. And we can see what is imaginary or what is not real, which is this. Okay, any questions? Any questions? Okay, if there are no questions, then it means we are all on the same page, you know. So that's done with operations. So let's look at sketching complex numbers, because you need to be able to sketch them. And when you are able to sketch them, then you are able to transition to your Euler form and your polar form and whatnot. So let's look at sketching and see how it looks like. And then if we can understand sketching, then we are good as done. Because now moving to Euler form, it's easy. Moving to the argument form will also be easy. Then now you can do fancy stuff on complex numbers, like taking the square root of a complex number, right? So let's look at sketching and see what we need to take away from there. So, well, my complex looks complex. Let's try again, complex. Now this looks better. So what you should be aware of is we have what we call the complex plane or the real imaginary plane. So we either call it the complex plane or it is the real imaginary plane. You know, the same way you have your Cartesian plane, your x and y plane, or x, y, and z plane. We also have the complex plane. How it looks like is this. On the horizontal axis, that's where we put the real part. On the vertical axis, that's where we deal with the imaginary part. For example, so let's say we are given that we need to plot z is 2 plus 3i. So here I can see that the real part of z is 2, and the imaginary part of z is 3, whatever which is multiplied by the I. So now I'm going to go to my plane and say, okay, cool. So we have a 2 and a 3 there. So the 2 lies somewhere here, if you had scale. And a 3 on the imaginary axis, the positive 3, so it should lie somewhere here. And then what we do is we draw a line from here, and we go down there, and they meet here. And we draw a line from the origin to where they meet, from the origin to there. And that's our complex number. We have plotted the complex number, and whoever is marking is happy. We know our stuff. And all what is left is for you to give them the magnitude of this cursor, or let's call it that line. You need to give them the magnitude, and that magnitude is simply the magnitude of the complex number. Remember that the magnitude of a complex number, we said it's the square root of the real part squared plus the imaginary part squared. So which means the magnitude of this complex number which we are given is simply the square root of the real part is 2, squared the imaginary part is 3. So there we get 4 plus 9, which is going to be the square root of 13. So we go and say, look, we know here it's just the square root of 13. And there's an angle. What is this angle? It's something which we will stress about in a few minutes. Any questions? Okay, let's give another example a shot. So let's say you now have z is minus 2, minus 2i, and we need to plot this. Well, let's get our plane up and running. Right, easy. And we know here, imaginary axis, and here we have the real axis. Positive, negative, positive, and negative. So let's see. We can see that the real part of z is minus 2, and the imaginary part is also negative 2. So we look at the real axis. Where is negative 2? It should be somewhere this side. That's where our negative 2 is. We look at the imaginary axis. Okay, we have negative 2 also. Negative 2 should be there. And then we now go and draw a line. We have a line here, another dashed line here, and wow, they meet here. So we need a line from the origin to there. And that's our complex number. And what is left is for us to give them the magnitude and the angle. So the magnitude we can easily give them. This is the square root of the real part squared, negative 2 squared, plus the imaginary part squared. So that's going to be 4 plus 4, which is just the square root of 8. And we can leave it as the square root of 8. And then when they ask us about the angle, well, we are coming there because we need the angle to fully plot our complex number. But now, the aim is for you to get a sense of how you actually plot your complex number. So let's give, let me see, 1 or 2. Let's give 2 more examples a try and see. Then we can move and see how we find the angle. So e.g., okay, so now we have this one. First things first, where is my real imaginary plane or the complex plane? So some groundwork. We can see the real part of Z is -2. And the imaginary part of Z is 2. And when you find the modulus here, you will get square root of 8. So the real part, we can see the real axis, it's the horizontal one. So we have -2. -2 should be somewhere here. Imaginary part is the vertical axis. And we see +2. So +2 should be somewhere there. And we do the usual, draw our dashed lines and do them even this side, make a point where they intersect, and then go and make a line from the origin to where the intersection is. And we need the magnitude of this cursor, which it is √8. The angle, well, we will look at the angle. And now let's say you are faced with the case where, let's come this side now. I hope I'm not moving too fast. So let's say they give us Z is 2. That's your complex number. So we know that Z is 2, well, that's only real. So that means the imaginary part was 0. So now if I try and draw my plane, it will be my 2 is here, but the imaginary part is 0. So that means all what I have is my complex number will move from the origin to there. And its magnitude is just going to be 2. And this is the real axis. This is the imaginary axis. Let's say now we have a case where my Z is -3i. So I don't see the real part here, which means the real part must have been a good 0. So sketch our Cartesian plane. So now I look carefully. Look. So the real part is 0. And the imaginary part is -3. So we're sitting here. So that means, okay, my cursor is just gonna go straight down like this, and it's gonna have magnitude 3. And the angle, we can clearly see theta will be -90 degrees. Okay, let me erase the angle now, but it is -90 degrees. And let's stress about it after this. Anyone who is lost? Do we have anyone who is lost? Okay, No one is lost, I'm happy. So now we have been plotting these complex numbers. And let's look at how we can find the angle. But before we find the angles, let me make a case why we actually need to find the angles. Because, we're not doing things for the sake of doing them. So now we are looking at the argument. This is not the argument which you guys have or which people have. The argument here is an angle. Yeah. Let me put it. We are looking at the angle. So when we are saying the argument, we are looking at the angle which the phasor makes with the positive real axis. So look, this is nothing really deep. Let's see. So this is the positive real axis. This is the positive imaginary axis, negative imaginary axis, and negative real axis. So when we are looking at the angle, we are always using the positive real axis as the reference point. So let's say the phasor is here. So the angle will be the angle from the positive real axis to the phasor. That would be theta 1. So if the phasor is here, then the angle will still be from here, but now going in this direction. Let's call it theta 2. So it's always the angle it's a reference angle from the positive real axis. So it's something you need to keep in mind. Make sure you are using the positive real axis as your reference point. Okay, so let's see why we actually need the angle. So let's consider a case where we have two complex numbers. Z1 is x1 plus i1, and Z2 is x2 plus iy2. And now the question can be, why do we even need to find these angles? Are we plotting these complex numbers because it's maths and we need to pass a course? And the answer is no. So you can do the operation of Z1 times Z1. Maybe let's say you find a case where you need to multiply Z1 by itself. You can do the FOIL, which we have been doing. And you can easily do the FOIL, But now imagine this is the same as Z1 squared. Now if I say Z1 cubed, so now you need to have 3 brackets, which you are multiplying. And I go and say, look, I want you to multiply this complex number by itself 5 times, which means Z1 to the 5. So you need to have 5 brackets, and that's in the exam. And you are trying to do this FOIL thing 5 times. And now let's say worst case, not the worst, but still a reasonable case. Now I'm saying, look, I want you to multiply Z1 by itself 100 times. So you are an engineer and you should be lazy, but smart. So doing 100 brackets, I don't know, you'll probably take a year to finish. So you will do 100 brackets in the exam, and that time the question is 4 marks. And you are making 100 brackets and you are asking for extra papers. It would be interesting to see. So immediately when we try to multiply complex numbers many times by itself, we now need the angle. Because if we have the angle, we can convert it to Euler form. And when we are in Euler form, when you raise a power, you are just multiplying the exponential part. and it's that easy, and you can easily convert it back to your x plus I, y. So when we have the angle, we can easily do this within minutes. Multiply the complex number by itself 1,000 times. It's just a matter of 2 minutes and we can do it. But if you don't have the angle, then it becomes a problem. So that's why we are motivated to say, look, we need to know the argument. And when we know the argument, then we can do things which we cannot do if we don't know the angle. For example, we can now find the square root of complex numbers, which is where we are going. Because if now they say find the square root of 3 plus I, this is not easy to find, but if they say 3 plus I squared, you open 2 brackets, you do your FOIL, and you get it. But this case, what about it? Well, can probably make you feel this way, which you shouldn't. So let's see what we do with arguments and see how they make our life to be easy, finding these angles. Right. So I'll share, let me draw it. Perfect. See, am I gonna have enough space here? For sure. So when we are looking at the argument, what we will look at specifically is what we call the principal argument. And by principal argument, remember argument, we said it's just the angle. So let me say the argument of Z, which is a complex number, is theta. So when we say principal argument, that angle which we need must always be between pi and negative pi. If it is out of this range, then the argument which you have is not a principal argument. So essentially, our principal argument is bounded. We are looking at the horizontal plane. Your angle is bounded. This is 0, and this is 180, and just below this is negative 180. So we are bounded. This looks deceiving. Let me not write it. It will look deceiving. But essentially, your angle is bounded between negative 180 and positive 180. If your angle is out of the range and you try performing computations like multiplying a complex number by itself 100 times, then you will get it wrong. So you must make sure your angle is correct. And I have a diagram which I'm going to draw for you, which will make sure that, look, we always have the correct angle. So let's see. Let's consider a complex number. Z is A plus IB. So here we can see that the A is the real part. So let's just say the real part of Z is A, and the imaginary part of Z is B. Let us draw our Cartesian, not Cartesian plane, but real imaginary plane. Let's see. Okay, so this is our real imaginary thing. So you should look at a complex number when it's given. You should look at the real part and the imaginary part. So if the real part is greater than 0, meaning it's positive, and the imaginary part is also positive, that complex number lies on the first quadrant. So we have the first Q, we have the second Q. Okay, see what's happening. Raise. Let's undo this. Okay, so we have the first Q, second Q, and we have third Q and the fourth Q. So when you look at your complex number, A plus IB, if your A is positive and your B is positive, then it means you're on the first quadrant. Remember, we are trying to look at the angles now, because you can tell by just quickly doing a rough plot where your complex number lies. So if it happens to lie on the first quadrant, then your theta, because remember now what we are trying to do is to find the argument. That's what we are trying to do. So your theta will simply be arctan of B over A. So we take the signs as they are. Right. And if you look at your complex number and you realize that, look, my A is greater than 0, the real part, but the imaginary part is less than 0, it is negative. That means you're on the fourth quadrant. And your theta, which will give you the correct principal argument, is simply arctan of B over A. Then now let's say you find yourself in the second quadrant, which then means your A would need to be less than 0. Your real part is negative, and your imaginary part is greater than 0. So this, your theta would be equal to your arctan, your B would be arctan of B over A plus pi. And then if you find yourself on the third quadrant, or you look at your complex number, the real part is negative, the imaginary part is also negative, then your principal argument will be theta is equal to arctan of B over A minus pi. So this is all what we need, good people, to make sure that we do justice when it comes to getting the correct principal value. If you can make this to stick in your head, you are going to save yourself a lot of time next year. And some of you, it's this year. Some of you, it's going to be next year and the year after. So make sure this year, you know. Didn't pick up those. So make sure that this, you know, let me write here and say, you will see this later when you're looking at this PDF. You must know, it will save you a lot of time and headaches. Okay, so let's look at a few exceptions. So this is one. Now let's look at what happens if the complex number lies on either the horizontal or vertical axis. Okay, so now let's say we are facing a case where the complex number doesn't come out as that, doesn't fall in the quadrant as we saw the quadrant. So let's say your complex number is 2, let's take this one. So let's say my complex number, when I plot it, it is here, right? Which means it's just Z is equal to, let's say, 3. Then my theta would be 0. Okay, that's done. Then let's say I plot my complex number and it comes out to just lie here. No. Then my theta should be pi over 2. And then let's say I plot my complex number and no, I plot my complex number. It lies here. My theta here can be, it is pi, it's 180, because we are measuring from the positive real axis. And now the last one. If you plot your complex number and your phasor faces in this direction, then your theta is negative pi over 2. Right, here, let's say exceptions. Okay, any question? Right, so let's use this, because it's one thing to say it, but it's another thing to use them. So let's phrase a question and see how we can use these. So let's plot this complex number. Z is 1 plus I. So it's easy to plot this. We have been doing it. So let's go. Come here and like that. And we can easily see the real part is 1. And the imaginary part of Z is also positive 1. So remember, positive real axis, try again. And here we have the imaginary part. So real axis, we are looking at a 1. There's our 1. Imaginary axis, we are also looking at a 1. There it is. And now we can draw a dashed line, that, and another one, like this. And they combine there. That's where they meet. Where they meet is where we need to draw the line from the origin to the intersection point. So there we go. And we need the magnitude of Z. If you remember, magnitude of Z is simply the square root of the real part squared plus the imaginary part squared. So we get square root 2. Square root 2 is the magnitude. Now, what is our angle? So we can see we're on the first quadrant. So let's quickly go back to our sketch and see how it really helps us. Where is it? Here, first quadrant, that's where the complex number is. The theta should simply be arctan of B over A, where B is the imaginary part and A is the real part. So now, if this is a test situation, you are supposed to fetch this diagram in your brain. So our theta is arctan of 1 over 1. And arctan of 1, you should remember from high school, it is tan of what which gives you 1. It must be tan of 45. 45 is pi over 4. So here, our angle, we can safely go and put pi over 4. And we are done. Whoever wanted this is going to be extremely happy. And guess what? When you can now plot complex numbers with their angles, we can now go to what we call the Euler form. Because what we were doing was the real imaginary form. So a complex number, we can write it in another form, which we call the Euler form. But before I go to the Euler form, I'm going to leave a note for you, which is going to be homework, which is make sure you know your special triangles that you should take as your homework. Make sure you know them off by head, that it is tan of what which gives me 1. It is sine of what which gives me square root 3 over 2. Those kind of things. You should know them by, well, you should recall them for sure. So let's see. So we said us knowing the angles allows us to move to what we call Euler form, which is another way we can represent complex numbers. So let me do this. So if you look carefully, what we have been doing is the real imaginary form, right? So now getting the angles pushes us to what we call the Euler form. So now we are looking at what we call the Euler form. And all what Mr. Euler says is that, look, so you have your complex number in standard form. So the real and imaginary form, they also call it standard form. So in standard form, our complex number, it is x plus I, y. And then Euler says, look, we can take this complex number and write it as z is r e I theta. This is what Euler is saying, where let me put it here, where your r is simply the modulus of z, or the modulus, we remember, it's just the real part of the complex number squared plus the imaginary part squared. Or for this case, it is just the square root of x squared plus y squared. And our theta is the principal argument. That's what Euler is saying. Let's take an example, e.g., the one we have done already, z is 1 plus I. So I need to figure out what is my r. My r, I can see it's the real part squared plus the imaginary part squared. So my r is simply square root of 1 squared plus 1 squared, which is the square root of 2. So this complex number, I know it is on the first quadrant in Cartesian, in the real imaginary plane. And I know when we're on the first quadrant, your theta is arctan of b over a, or arctan of the imaginary part, which is 1 over the real part. So we get arctan of 1, which we have obtained to be pi over 4. So therefore, in Euler form, this complex number is the same as r, which is square root 2, ei theta, which is pi over 4. And now whoever is marking is happy, you can write this in Euler form. And guess what? When you can write Euler form, you can easily write polar form, which that word should sound familiar. So let's look at polar form. So we now have the Euler form of a complex number. We also have the standard, which is standard form, which is also called the real imaginary form. That's what we've been dealing with. Then now we have the polar form, which is nothing deep actually. And the polar form, all what it is it says, look, so you should move from z is y, from z is equal to x plus iy. And then now when we are in polar form, I need to see z is r times cos theta plus I sine theta. This is all what polar form is, where your r is simply the modulus of z, and your theta is the principal argument, which we have seen how to obtain. So you see, for example, this complex number here, we obtained the theta as pi over 4. If we now wanted to write, if we now want to write it in polar form, all what we'll do, we'll have z is equal to, what is the r? We have obtained the square root 3, which is just the modulus of the complex number, times, what is the theta? Pi over 4. So cos of pi over 4 plus I sine of pi over 4. And this is your complex number in polar form. And guess what? It is easy as you think. Any questions? Any questions, good people? Okay, so now let's see how this is useful. So let's take an example and then write a complex number in Euler form. So, example. So we given z is -1 plus I. And now we need to write z in Euler form. So the first thing we know, we need r, and r is the modulus of z, and modulus of z, it is the real part squared plus the imaginary part squared, which gives us square root of 2. Right. And now let's plot our complex number roughly, get an idea where it is. So if you look at -1, it is here. And you look at +1, because the real part of z is -1, and the imaginary part of z, if you look carefully, it is +1. So real part, -1 is there, +1 is there for the imaginary part. And tie these together. This is where you get the common intersection point. And our complex number should be here. And all what we needed to take away was, okay, this is on the second quadrant, you know. Good. So now let's think. We need the argument. Modulus we already have. What is left is our theta. And this is the second quadrant when you plot this complex number. You quickly go back in your brain and you go to this diagram and you are like, so when it's the second quadrant, it is arctan of b over a plus pi. So let's go and use this. So theta is for the second quadrant, arctan of the imaginary part, which is 1, divided by the real part, which is -1 plus pi. So this will be the same as arctan of -1 plus pi. And you should know your trig identities that we can actually pull out the -1. And arctan of 1, we know it is pi over 4. So the negative makes it negative pi over 4 plus pi. And if you add these, you should get 3 pi over 4. So this means this angle here is 3 pi over 4. And now we can go and write it in Euler form, because we know Euler says we need R and the principal argument, and we are done. So our Z will be our R square root 2, I, our theta is 3 pi over 4. Okay, guys, any question? I need at least someone who has a question who's like, look, what did you do here? Any questions? Are we still in the session?
Yes, we are.
Okay, so the silence to me, it says, look, we understand what you are doing, which is great. So this is the Euler form. And if you had to go to the polar form, it would be just a matter of recalling that actually e to the I theta is the same as cos theta plus I sine theta. If you don't recall, then I'm telling you, which means if we have I 3 pi over 4, this means this is equal to cos 3 pi over 4 plus I sine of 3 pi over 4. And now when you need to write this in polar form, we just need to copy this and put the R front, and we are done. So let's copy this, paste it here, put some brackets. My R is square root 2. And this is my Z in polar form. So we now can write our Z in polar form, standard form, and in Euler form. And if you want to go back to standard form, you just need to figure out what is cos of 3 pi over 4, right? So let me see, 3 pi over 4, 180 divided by 4 by 2 is 90, 45, 45 by 3, it is 90, 135. So for example, what is cos of 135? You need to figure that out, special triangles. And what is sine of 135? Reduce that to an acute angle, and you'll be able to figure that out. So that's now more of high school stuff. So let's see what happens. So now how this is useful is you are able to take the roots of complex numbers using these, or you are able to take the powers of complex numbers. Let's see an example. Give me, let's see. So now look at what I was saying, and you'll see that actually what we have been doing is important. So number one, it's going to be able to assist us with factorizing, and it's going to be able to assist us with raising powers to complex numbers. So let's say they say find -1 plus I to the power of Let me see. Let me put 8. So multiplying this 8 times is not going to work. So why not take its equivalent? Because we know that -1 plus I in Euler form, it is this. That's what we were doing on the previous page. So you would take your number, write it in Euler form. Then now, which means what we can actually do, we can substitute it and then put the 8. And now when you simplify this, it is simply square root 2 to the power of 8 times I. The 8 will multiply with the 4. So the 4 will cancel and we'll have a 2. So it will be 6 here. Oh, in fact, let me write it like this, 3 pi over 4. And then the 8 is now here. And this will simplify square root 2 to the 8e to the I times 6 pi. Okay. And let's see what this is going to be. So we now have, you remember that this is the case. Square root is simply the power of half. So let's make life to be a bit easy. And I 6 pi. So remember that we said e to the I pi, I theta is cos theta plus I sine theta. So above here, what we have is going to be 2 to the 8, not 8, but 4 now, I 6 pi. So what we have is 2 to the 4, that's 16. So we have 16 times cos of 6 pi plus I sine of 6 pi. So we know that sine of 2k pi or sine is periodic with period 2 pi. So this is going to be 0. Let me quickly draw you this, it's nothing out of this world. Sine is like this. So this is 2 pi. So meaning at a multiple of 2 pi at 4 pi, sine, this point here will be here at 0. And for cos, let's see, we can squeeze it in here. Cos looks like that, and something like that. So which means at every multiple of 2 pi, cos will be at 1. So this means that this part here becomes 0. And this part here is 1. So our answer is simply 16. So if you take that complex number, multiply itself 8 times, you are going to get 16. So if I made a mistake, please shout out.
Yes.
Yes.
Can you please explain the example? Like I missed something. Step number 2.
Yes. So step number 2, remember that this complex number is exactly the complex number we're dealing with on the previous page. And already we figured out what our principal argument is. So now this side, because they are trying to make me to multiply a bracket 8 times, which is a lot of work, I chose to take that complex number and write it in Euler form. And now instead of having -1 plus I in brackets, I now have square root 2 e to the I 3 pi over 4. And I just distribute the exponent in exponential laws. And this is what I eventually end up with. Did I answer your question? Or let's zoom in into step 2.
Yeah, I see my mistake.
Okay, sweet. Right. So look at how beautiful this is. You have a complex number and you multiply itself by 8 times, and voila, at the end of the day, it becomes 16. Profound. And if you look at the first chapter of your maths 2026, 2011, and 2014, you do the polynomials, not polynomials, but the roots of complex numbers. Say, for example, they say take, or they say find the square root of -1 plus I. This is not so obvious, but now we can make it easy by going to our Euler form. So they usually say find and plot. And plot this. So we can go to our Euler form. We know that -1 plus I is square root 2 EI 3 pi over 4. So which means what we are looking at is square root of 2 EI 3 pi over 4 to the power of 1 over 2. That's the square root. All what I did was to substitute that complex number by its equivalent. Now I can distribute the exponential part. So I have the square root of 2 raised to the power of 1 over 2 EI. This is now going to be 3 pi over 4 multiplied by 1 over 2. But here's what we do then here. We know that sine and cos are periodic with period 2 pi k. So if we add from our angle, if we add 2 pi k, which is like, if you remember in high school, it was k 360. When you were saying theta plus k 360, the general solution, that's exactly what we are doing here. And then you have that half of yours. And then what we have will be put in the 2. So we get 3 pi over 4 plus pi k. So now, since I was raising to the power of 1 over 2, my plot should have 2 phasors. So if I was taking the cube root, I was going to have a diagram which has 3 phasors. If I was taking the, let's see, if I was taking the 4th root, I was going to have 4 phasors. So now our focus is, we now need to plot this complex number, this one, and this is supposed to be 8. Okay, hope you can see why this and this. Okay. So now we need to try and plot this complex number. But one thing you need to remember is that this here still needs to be the principal argument. So let's copy this and go to the next page. Do a rough plot, and the details are not really a problem now. So the aim is for you to be able to get to this. And following from there will be easy. So our angle still needs to be the principal angle. And remember that we said it must be between pi and negative pi. So since we took the square root, we need two phasors. So the easiest k value to choose usually is k is 0. So which means actually we need two k values, because our complex number was z, we raised it to the power of 1 over 2. So if we raised it to the power of 1 over n, we're going to need to choose n k values, which means we would have n phasors. Not phasors, let me call them cursors when we draw. So you'd need n cursors. So now since we took the square root, which means it's just 2, we need 2k values. So let me make this smaller and put it here. So the easiest k value to choose is k is 0. And after choosing k is 0, you plug it in the angle and see if it fits the specification. So when we put k is 0, our angle becomes 3 pi over 8. And 3 pi over 8, we know very well it is less than pi, but greater than negative pi. Sweet. Let us try k is 1. Let's put k is 1. So if you put k is 1, you have 3 pi over 8 plus pi. So already you can see that we are exceeding pi by this. So k is 1 does not work. It is out. So now, since it doesn't work, let's go to the negatives. Let's go to -1. Just what is below 0? Let's take k is -1. If we take k is -1, we have 3 pi over 8 minus pi. And let me see, 8. This will give us -5 pi over 8. And the question is -5 pi over 8 between negative pi and positive pi? It's a question for you guys. Is -5 pi over 8 between negative pi and positive pi?
Yes, it is.
Okay, great. So thumbs up. We are okay here. So then, if you draw your phasor, let's see. If you draw, come here. If we come here, why? If we come here and we look, so look at how beautiful this is. So this angle here, can we all agree that it's on the first quadrant? We are engineers, guys. You should have a sense of being able to quantify things. So by looking at this angle, can we agree, this one, that this angle lies on the first quadrant?
Yes.
Okay, great. So that means we might be looking at a phasor which is just like this. And that's the theta, which is 3 pi over 8. And looking at this one, can we agree that this angle lies on the fourth quadrant?
Yes, sir.
Great. So this is somewhere here. And the angle is like that, and that's why it's negative. We are looking relative to the positive x, not x-axis, but real axis. So our theta is -5 pi over 8. And we know the magnitude of these cursors. It is just the square root of 2, which is just 2 to the 1 over 4. We have 2 to the 1 over 4. And this is about it. You are now able to plot even the square root of a complex number. Imagine. Okay, any questions, guys? Any? Any questions?
I have a question.
Yes.
I don't understand. Why did you add the period like 2 pi k to the angle? Why did you add it?
It doesn't change. Do you agree? Okay, let's do this. So the period doesn't change anything, you know. So we want to be able to see the complex number even when there's a period. Let's see. Right, do you agree that, think about this carefully. You agree that sine of theta plus 2 pi k is just the same as sine theta, and that cos theta plus 2 pi k is cos theta. Do you agree? As long as my k is an element of, if I can make it an integer, then this will always hold. Even if I can put k as 1,000, I will get the same answer as when I just have theta only. Agreed?
Yes.
Okay, great. And e to the I theta, guess what? It is cos theta. So it's a periodic, it's a sine, not sine, but it is a sinusoidal combination. So, which means if I say EI theta plus 2 pi k, it is just the same as cos of theta plus 2 pi k, flip them there, I sine theta plus 2 pi k. And we know that these on the right-hand side, they are still the same as that plus I sine that. And this is equal to I to EI theta. So essentially, we are just introducing periodicity. It doesn't change anything. It does not. So for raising complex numbers to the nth polynomial, or let's say taking the root of a complex number, you'll need to introduce the periodicity. So let me say this here. Let me make a note here. So you must introduce if taking when, not if, sounds better. When, let's use when here, because you shouldn't be confused by what is written. So you should introduce when taking, let me call it the nth root. So this can be square root, cube root, or whatever. But now when you are taking the nth root, please introduce the period, and it will work out just okay. Because when you look at the complex number, if you draw a sine wave and convert this, I'm avoiding going where I'm going. But let's say if you are taking the nth root, please introduce the period. It doesn't change anything. But then after introducing the period, you must be like, okay, I was taking the nth root. What is the n? The n is 2. My diagram should have 2 cursors. The n is 3 if I'm taking the cube root. I was supposed to have 3 of them. If I was taking the fourth root, I was supposed to have 4 of them. And what you need to remember is that This angle here, after introducing that root, whatever it is, the angle here must still be a principal angle when you choose your K values. So which means in the exam, everyone will have the same K values because we are all looking for the principal argument. So the K values are restricted. For example, if we choose 0 here, we get the correct value. It falls within the range. If you choose 1 out, so which means you must go down. If you choose -1, it is in. If you choose -2, the data we get is going to be out of range. And you can clearly see it's only 0 and 1 work. So you are constrained to having 2 of these. Okay. Any questions? Let me come this side. It has been a long one. Any questions? Right. Because if we don't have questions, you guys should be able to at least look at your study guide and not be scared of. So let me do one last thing around sketching. Let's see what I can do in 5 minutes. So for the first part of the course, you will also be doing some sketching, which is easy, really, because you have done complex numbers. So for example, let me call it complex regions. So for example, let's say they are saying sketch the real part of Z is greater or equal to 1. So now you need to go and where is purple? Here's purple. Here's my complex plane. I know we have the real and the imaginary this side. So now I can see the real part is 1. So 1 is somewhere here. And they are saying greater or equal to. So I need to draw a line there. So let's draw a line there. So since it is included, I need to draw a solid line at the real part, which is 1. And they're saying greater than. So meaning I know the real parts of a complex number. All the other ones which are this side, they are greater than 1. And this is my region. And whoever wanted this is happy. Right. So let's see another one. Let's make this to be smaller. So let's say they say, look, now we need you to find the imaginary part of Z is less than or equal to 1. So let's pull our complex plane. Where is the imaginary part of Z where it is 1? It's somewhere here. There's my 1. Let's put it here. There's my 1, imaginary part. Because remember, imaginary axis, real axis. So it is included. So I will draw a solid line straight there. And now they are saying less than. So I know all the imaginary parts which are below 1. That's what they are saying. That's what they are looking for. So we shade below the 1. That's the less than. And this is the region they are looking for. Okay. So they wouldn't want to ask us a a region which is this simple. So let's say they combine it. They're like, look, so how about you deal with the real part of Z is between 1 and -1, but excluding -1. So now what you need to do is to pull your real imaginary plane. And let's look at where there is what? 1. So this is the real axis. So our 1 is somewhere here. So, and it is included. So let's draw straight line. Let's look where there is -1. It is somewhere here. And it is excluded. So we'll draw a broken line. And they are saying they are looking for the region in between. So this is that region. That's what they are expecting us to plot. Okay. So that's the region. So let's look at one last case and we can call it a day if there are no questions which are arising. Let me see. Let's take the imaginary case. So I'll take straight from your tutorials for Maths 2016/11 and 14. So there's one where they're saying we need to sketch the imaginary part of Z less than or equal to pi, but greater than -pi. So we go down, imaginary axis, I am looking for positive pi, so it is there. And it is included. So when I draw a line which is solid. And now I need to look for -pi, which is somewhere down there. And it is not included. So I need to draw a broken line, dashed. And then guess what? What we are looking for is the region in between. So this is all what we are looking for. It's this region. Okay. So you should check those set questions out. They are quite easy. It's around number 10. And you can try those, and you can do also number 11, but what we did, and number 12 you should be able to do. And you should be able to do number 12. Yeah, I said that. And 15, you should be able to do a mouthful given what we did if you go and look at your study guide. But let me pause here and come back and see if we have any questions. It is chatting time. No need for you to feel tension. So unmute and let's hear what you have to say. Okay, if you guys have no questions, we can
have
short. Yes.
Hello. Yeah,
Yes.
I just hear you mentioning the study guide. Which study guide is that? Are we going to get new study guides for this year for Maths 2026 or 10/16?
Yes, so you will get study guides. They will give you, but already there are PDF versions. So that's what I'm referring to, which some of you should have PDF and already assume. And the PDF version will pretty much be the same as the one which you are going to obtain, but it will be printed. So the third questions I'm referring to, they are on the PDF version one. But as soon as you get your hard copy, you should be able to see. But I think for now, for you to be able to start working and looking at the questions I was referring to, you can get the study guide, the PDF one, drop a message in the groups, and I'm sure your classmates will be able to share, and you can start looking. Because if you're gonna wait for what, week 1, week 2, it defeats the purpose. Okay, any questions? Or maybe let me say any compliments. Let's see. Let me stop the recording.